Hello, I welcome you all. The problem reads, a large crate having a mass of 200 kg is moved along the floor using a series of 150 mm diameter rollers for which the coefficient of rolling resistance is 3 mm at the ground and 7 mm at the bottom surface of the crate. Determine the horizontal force P needed to push the crate forward at a constant speed. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. We are still dealing with rolling resistance, and we defined what it is in the previous video, and we said the rolling resistance is the opposing force, on a rolling body in motion when the rolling body is in contact with the surface. So this is the opposing force on the rolling body, and this happens when the rolling body is in motion and in contact with the surface. Okay, so let me draw what I'm talking about here. So we have a body like this, of mass W, and imagine this body is moving, and its motion is being maintained by this force P. And imagine this body is rigid. Let's say this cylinder or this rolling body, we call it just rolling body. Imagine this rolling body is rigid, and then we have the surface that is not as rigid. So this surface, the surface is not rigid compared to the rolling body. So we are going to have some deformation, and therefore instead of having the normal force coinciding or in the same vertical direction like the weight, it is going to be at a side, at a side, right? But it will be concurrent with the three forces, right? Then we are going to have, when this happens, we'll have what we are calling the angle of the rolling resistance, as well as another parameter that we are calling A, and this is nothing but the coefficient of rolling resistance. Okay, so in this problem we've been told there are two coefficients. There is one on the surface where these the rollers are rolling on this surface, and on the surface here we've been told on the surface it is 3 millimeters. So this coefficient here, A, is 3 millimeters. And then on the crate also there is some deformation going on. So there is deformation on the ground. Okay, there is deformation on the ground being measured by this coefficient of 3 millimeters. There is also deformation on the crate, on the bottom of the crate, and it is 7 millimeters. So we have been asked to determine the horizontal force P needed to push the crate forward at a constant speed. Alright, so this is basically what is happening. I hope this is clear. Alright, then let's write down some assumptions. So these are the assumptions. Okay, the first one is P. This P that is being applied is P is evenly. It's assumed that P is evenly distributed across all the rollers. The second one is the weight W is also evenly distributed. On the rollers. And if this is the case, then we can model this all the rollers as just a single roller. Okay, so now we have a crate like this. We have a crate, and this crate is experiencing a push of magnitude P, and it has a weight W. Okay, so we're going to have a reaction P and a normal force N, right? This is what we expect, right? But what is happening right now is the crate is undergoing some deformation as well as the surface. So let's show this on the wheel. So we have this resultant force here. Okay. If this point here is B, let's call this as NB. And this NB has components P and N. Okay. Alright. So this is the force that is causing the deformation, or there's a deformation here on the crate, and we have a component P that is resisting the motion of the crate. Okay. So let's draw this wheel so that we show this. So we still have the same component NB, but this NB has components. It has components N, and this N is equal to W, right? So this is W, and then it has another component we are calling P. Okay, so if this is our center there, we are going to have something like this. Okay, with a normal like so, and then we'll have an angle there with a vertical. We'll have an angle with a vertical, and this angle we are calling it theta B. And then we also have this deformation that we are measuring using the coefficient A. I'm calling A subscript B, and is equal to 7 millimeters. So this is the deformation on the crate. Okay, so it is the one that is retarding the motion of the crate as it is being pushed. Okay, and then we also have another deformation on the ground of 3 millimeters, and we have a reaction in this direction like this. Okay, like this. Let's call this point here is our A. Therefore this is going to be our NA, and it also goes directly to this point here like that. Okay, let me redraw it properly. Okay, I redraw it properly. Let's imagine it is somewhere there like that. Okay, so this point here we said is A, and this is NA, and then we have this point going through like so, and then we have the vertical. Okay, then we have this vertical, and then we have this angle here we are calling theta A. All right, and then we have this distance here, and this one is a coefficient A subscript A, and is equal to 3 millimeters. Okay, and then we know already the radius of the radius for this is 75 millimeters. Okay, so with this information we can go ahead and find the angles quickly. So we have theta A is going to be equal to sine inverse of 3 divided by 75, and if we calculated the angle, it gives us a 2.2924 degrees. Sine B, sine inverse of 7 divided by 75, and this gives us a 5.3554. Right, so with this information, what we are going to do now is apply the equations of equilibrium so that we find this value of P that we are supposed to apply so that we overcome these retarding forces that the crate and the grounds are experiencing. I mean that the wheel is experiencing due to the deformation on the crate and the deformation in the ground, on the ground. So summation of moments about point A equal to 0, anti-clockwise being our reference. Okay, so what do we have? We have W times AB plus AA, and then minus P times r cos, this r is the radius for the roller, which is 75, r cos theta b plus r cos theta a. Let me move this a little bit backwards so that I have some space. Okay, then equal to, still not enough space. I'll need to move it backwards again. Let me do this. Alright, I move it again, maybe up to there. Yes, this equal to 0. Alright, and therefore our P is going to be equal to WAB plus AA divided by R we can factor it out, and cos theta b plus cos theta a. Okay, replacing these values there, we'll have P is equal to W is 200 times 9.81, then in brackets, I'll not convert this to meters because I have millimeters underneath. They can cancel. R is in, I'll leave it in millimeters, and also these values of AB and AA. So we have AB equal to 7, then AA equal to 3, and then divided by 75. Cos theta B we said is a 5.3554 degrees plus cos 2.2924 degrees. Okay, when we do the calculation, we'll find that the value of P is equal to 131.14 newtons. So this is the magnitude of P that we need to push the crate forward at a constant speed. I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing, sharing, and give me a thumbs up. Bye bye, and see you in my next screencast.